Hi everyone, my name is Tanesha Aganaputri. In this opportunity, I would like to introduce our project entitled Occupancy Effect on Thermal Comfort in Sglc 7B3 Classroom. This study was conducted as a part of our coursework in Communication Network, where we implement IoT-based monitoring system to analyze real environmental data in indoor spaces. Through this research, we aim to understand how classroom occupancy influences thermal comfort conditions, particularly in a tropical educational environment. This project was conducted collaboratively by our group members, whose names are listed on the screen. Each member contributed to different aspects of the research, including data collection, system development, analysis, and reporting. Classrooms are essential spaces for face-to-face learning activity and play a crucial role in supporting academic success. A comfortable classroom environment significantly affects the concentration, productivity, and learning performance of both students and lecturers. One of the most important factors influencing indoor comfort is a thermal comfort, which is affected by environmental conditions as well as occupant density. As the number of occupants increase, internal heat within the classroom also increase due to the human metabolic activity. Therefore, understanding how occupancy affects indoor thermal conditions is important to ensure an optimal learning environment. Based on this motivation, our study investigates the impact of occupancy on temperature and humidity using an IoT-based monitoring system. According to Ashrae, thermal comfort is defined as a condition of mind that expresses satisfaction with the surrounding thermal environment, and it is primarily assessed through this subjective evaluation. Thermal comfort is a key component of indoor environmental quality, and it is closely related to other comfort aspects such as acoustic, visual, and air quality. Several environmental parameters influence thermal comfort, including air temperature, relative humidity, and air velocity. These parameters interact with a building design and mechanical system to determine how comfortable an indoor space feels to its occupants. In occupied indoor spaces, such as classroom, human occupants act as an internal heat source. As occupancy increases, metabolic heat generation also increases, that leading to the higher internal heat gain. This condition can raise the perceived indoor temperature and potentially reduce the student comfort and focus during learning activity. Therefore, occupancy plays a significant role in shaping thermal conditions, especially in classrooms located in tropical climates. Based on the background we discussed earlier, the study has three main objectives. First, to analyze the effect of occupancy on indoor temperature and relative humidity. Second, to compare thermal conditions during occupied periods and after the class is vacated. And third, to evaluate the effectiveness of IoT-based monitoring system for real-time environmental data collection. Through this objective, we aim to better understand the relationship between occupancy and thermal comfort in the Sglc 7B3 classroom.
For literature review, we have thermal environmental condition for human occupancy based on a shared standard 55. Thermal comfort is influenced by environmental condition and occupant-related factor. With air temperature and relative humidity as the key parameter, air temperature affects heat exchange between the human body and the environmental, while relative humidity influences with evaporation as the main heat dissipation mechanism. High humidity reduces evaporative cooling, causing higher perceived thermal stress. Therefore, real-time monitoring of temperature and humidity is essential to assess thermal comfort and support adaptive HVAC control. Next, occupancy and heat load metabolism. Occupancy significantly contributes to the internal heat load of buildings because each occupant generates metabolic heat that is released into the indoor space. As the number of occupants increases, the total amount of heat generated within the also rises. In addition to occupant density, the during of occupancy influences the accumulation of heat, which can affect indoor thermal comfort condition over time. This relationship between occupancy level and heat generation is commonly represented by metabolic rate, which serves as an important parameter linking human activity to HVAC system performance and overall thermal comfort. Next, we have heat index. The heat index represents the apparent temperature perceived by human as a result of the combined effect of air temperature and relative humidity. It was developed to better describe human heat stress, particularly under high humidity condition where the body ability to dissipate heat through sweat evaporation is reduced. The concept of the heat index is based on Steadman's human thermoregulation model and is commonly approximated using the Rothfuss polynomial regression equation for practical application. And then we have equation like this. In environmental monitoring studies, the heat index can be directly calculated from temperature and relative humidity data obtained from sensor. In enclosed space, increase in occupancy lead to higher air temperature and humidity due to metabolic heat and moisture released by occupants, which consequently result in elevated heat index values and higher perceived thermal stress. Next, IoT-based monitoring system. In this system, we using the HD22 sensor, ESP32 microcontroller, and Blink platform. The IoT-based monitoring system integrates environmental sensing, data processing, and real-time visualization to evaluate indoor thermal condition. In this system, the DHT22 sensor is used to measure air temperature and relative humidity due to its adequate accuracy, stability, and ease of integration with digital and IoT platforms. Variation in occupancy influence indoor temperature and humidity through metabolic heat and moisture released by occupants, which can be consistently captured by the DHT22 sensor and used for further thermal analysis such as heat index calculation. The ESP32 microcontroller functions as the central processing and communication unit, providing sufficient computational capability and integrate wireless connectivity and flexible sensor interface to support real-time data and acquisition and transmission. Sensor data are transmitted to the Blink cloud platform, which serves as a centralized system for the data reception, storage, and management, while the Blink mobile application visualize temperature, humidity, and heat index data in real time. This integrated IoT architecture enable continuous monitoring of indoor thermal condition and support the assessment of occupancy-related thermal comfort. While the Blink mobile application visualize temperature, humidity, and heat index data in real time. This integrates IoT architecture enable continuous monitoring of indoor thermal condition and support the assessment of occupancy-related thermal comfort.
Moving on to our research method. To ensure the validity of our data, we employed a quantitative approach using a field observational design. This means that instead of relying solely on simulations, we collected data directly from the actual study site, which is the classroom, while regular activities were taking place. For our experimental setup, we defined three categories of variables. First is our independent variable is the occupancy level. We are specifically looking at how the number of students inside the room fluctuates and influences the environment. Second, our dependent variables are air temperature and relative humidity. These are the two primary metrics we are tracking to determine the thermal comfort index. Third, to ensure the consistency, we established control variables. We kept the air conditioner set point constant and maintained a fixed system configuration and sensor type throughout the observation period. Next, for the study location, we needed a space that experiences a significant changes in crowd density. We chose room 7B3 on the 7th floor of the Sglc building, Faculty of Engineering, Universitas Gadjah Mada. This room features a capacity of around 80 students. This high capacity is crucial for our experiment because it allows us to observe a wide range of occupancy levels, which is our independent variable, while fluctuating from an empty room to a full class. As you can see in the bottom right, the room utilizes a centralized air conditioner system. We documented this image because it was essential to ensure our control variables remain consistent throughout the data collection process. Next, to make this system work, we utilize three key components that handle the data from acquisition to display. First, for the data acquisition, we use the DHT22 sensor. While if you ask why we chose this sensor, because it can simultaneously measure both air temperature and relative humidity, which is our two main dependent variables with higher accuracy than the standard DHT11. Next, after the data acquisition, the data is processed by the ESP32 microcontroller. This acts as the brain of our system. Its primary role is to read the signals from the sensor and, crucially, use its built-in Wi-Fi module to transmit that data to the internet. Finally, for the user interface, we utilize the Blink platform. This allows us to monitor the classroom's thermal conditions remotely in real time via a mobile dashboard. Next, let's look at the operational flow of our system, which is divided into 5 stages. It starts with sensing, which is the DHT22 sensor reads the physical temperature and humidity parameters from the room. Next, after it sends the data, we process the data using the ESP32. The ESP32 doesn't just pass the data along. It converts the raw readings and actually calculates the heat index, which gives us a better measure of thermal comfort than the temperature alone. Then we move to encapsulation. This is the software side where the processed data is packaged using the Blink virtual write function from the code and assigned to specific virtual pins, which is V0, V1, and V2. These virtual pins have their own data or variables. The V0 is the temperature, V1 is the humidity, and V2 is for heat index that they get from the ESP32. Once all this data is packaged, we enter the transmission stage. The ESP32 uses its Wi-Fi connection to push this data to the Blink cloud. And for this Blink cloud, finally we have the visualization. The Blink smartphone app subscribes to the cloud data and displays the real-time temperature, humidity, and the heat index values to the user. So we can see all those three variables from our phone, anywhere, anytime. We can see it on this Blink smartphone app.
The next section presents the results obtained from the field observation. As previously described, the measurements were conducted in classroom 7B3 of the Sglc building under two main
condition during classroom occupancy and after the class session ended. The analyzed parameters include air temperature, relative humidity, and heat index, indicator of thermal comfort. There is a table presented to compare the average values of these thermal parameters between occupied and unoccupied condition. As shown in the table, during the period from 1414 to 1445 Western Indonesian time, when approximately 70 students present in the classroom, both air temperature and heat index values were higher compared to the post-class condition. In contrast, relative humidity was lower during the occupied period than when the classroom was empty. Moving to the next slide, two time series graphs are presented. The graph on the left illustrates the variation of air temperature over time. During the lecture session, the temperature remained relatively stable within the range of 25 to 26 degrees Celsius. After the student left the classroom, the temperature decreased quite rapidly, indicating a reduction in internal heat loss generated by occupants' metabolic activity. Meanwhile, the graph on the right shows the variation of relative humidity over time. In contrast to air temperature, relative humidity increased after the class ended. This phenomenon can be explained using psychometric principle, where a decrease in air temperature leads to a reduction in saturation vapor pressure, resulting in an increase in the percentage of air saturation. The following slide presents scatter plots illustrating the relationship between heat index, air temperature, and relative humidity. Based on the scatter plot between heat index and air temperature, a nearly linear relationship can be observed, where an increase in air temperature is followed by an increase in heat index. This indicates that air temperature is the most dominant parameter influencing perceived thermal comfort in the classroom. In contrast, the scatter plot between heat index and relative humidity shows a wider and nonlinear data distribution. Changes in relative humidity do not result in proportional changes in heat index. At lower heat index values, relative humidity tends to be higher, whereas at higher heat index values, relative humidity tends to be lower. This result suggests the lower relative humidity contributes to thermal comfort perception. Its influence on heat index in this study is secondary compared to air temperature. During high occupancy condition, metabolic heat generated by occupants increases air temperature, which directly raises the heat index, even though relative humidity does not increase significantly. Conversely, when occupancy decreases, the air conditioning system operates more effectively in reducing air temperature. This temperature reduction leads to a decrease in heat index, while relative humidity increases due to reduced capacity of cooler air to hold water vapor. In this slide, the measured thermal conditions are compared with commonly used thermal comfort standard, namely SRI standard 55 and SNI. According to SRI standard 55, the recommended air temperature range in cooling mode is between 23.5 and 25.5 degrees Celsius, with a recommended relative humidity range of 30 to 60%. Meanwhile, referring to SNI, which is more applicable to tropical climate conditions such as Indonesia, the thermal comfort zone lies within a wider air temperature range of 20.5 to 27.1 degrees Celsius and a relative humidity range of 55 to 60%. Under occupied classroom condition, the average measured air temperature reached 25.65 degrees Celsius. Although this value exceeds the air conditioning set point of 24 degrees Celsius, it is still technically within the upper limit of the comfort zone according to both SRI and SNI standard, particularly within the comfortably warm category. However, the average relative humidity of 65% exceeds the upper recommended limit of both standards. This elevated humidity level indicates a potential reduction in perceived thermal comfort even though the air temperature remains within acceptable limits.
Based on the result of this study, we can conclude that classroom occupancy was found to have a significant influence on thermal comfort condition in the Sglc 7B3 classroom. When the classroom was occupied, air temperature and heat index values increased due to a metabolic heat generated by occupants. After the class ended and the room became vacant, the air temperature decreased as the cooling system operated more effectively. Although the measured temperature were generally still within the acceptable comfort range for tropical standard, the relatively high humidity during occupied periods may reduce the perceived thermal comfort. Overall, this study demonstrates an IoT-based monitoring system can reliably support real-time evaluation of thermal comfort in classroom environment. This study highlights the importance of considering occupancy in evaluating thermal comfort in classroom. Thank you for your attention.